Hi everyone, this is the first video for section 4.2 and 4.3. So we're going to combine these sections. We're not going to talk too much about exponents from section 4.2, but definitely read over it. Make sure that you remember all of these properties and can use them. This is something that you should have learned in high school algebra, so either high school algebra or college algebra 1320. So we're not going to spend too much time on it. Okay, so first off, what's the definition of the exponent of we're raising something to a power, really? So if we have two whole numbers, then we can, two whole numbers, a and m, we can raise a to the power of m and write it like this, right? A to the m is just where you multiply m factors of a together. So this is the definition. So similarly, right, if we have, well, we'll do a couple examples. I'm sure that you've seen this before, but if we have a to the first, right, that's just a because there's only one factor of a there. Let me write it. A to the first equals a squared is a times a cubed is a times a, and so on, right? This is a general definition that works for any whole number. Okay, so that's the definition. And then we have all of these properties. So these are the properties that the book really highlights. And you need to be able to justify or prove any of these properties. So we're just going to go through some of them. So first, we're going to go through this one. So you should be able to prove these using either the definition of exponents or the properties of multiplication, typically the associative and commutative property. So a to the m times a to the n. Well, we know that a to the m is, let me see how we wrote this. Okay. Oh no, I erased the whole thing. A to the m times a to the n is a times a. So this is m factors, right, just based on the definition. So that's a to the m. And then we have a to the n, which looks very similar. This is n factors. Okay, so this is just the definition. Of exponents. Okay, so that's just what we get from the definition of exponents. So now we're going to use the associative property of multiplication, which just means you can rearrange the parentheses, right? So this is just a times a, and we can just combine them all, right? So we combine this into the first n factors and the first n factors. So this is just n plus n factors, right? Because it doesn't matter what order we multiply them in. We don't have to multiply the first n together and then the second n together. We can just multiply them all. So this is not commutative. So this is the associative property. Okay. And then lastly, right, this now is just m plus n times that we multiply a together. So by definition, that's just a to the m plus n. So then this last one is again definition of exponents. Okay, so this is how you do that first property, right? So we use the definition of exponents, the associative property of multiplication, and the definition of exponents again. Okay, so the next one I want to talk about is this a to the minus n. So this, yeah, is this a to the minus n is 1 over a to the n. A lot of these other properties follow really similarly to this one about when you multiply exponents, you actually multiply something raised to two different exponents, you actually add the exponents. A lot of these other properties follow similarly, so I would recommend doing this, right? Actually writing it down for each of these. But like I said, we're only going to talk about a few. So the next one we're going to talk about is a to the minus n is 1 over a to the n. So this one is more of a pattern. So whenever you justify these things, you should not ever just pick some numbers and show that it works. That's an example, not a justification. A justification, if we're saying that this works, right, we define this for any whole numbers, a and m, right? So this should work for all of the whole numbers. So showing me that it works for a particular example is not the same as showing me it works every time, right? We can have counter examples that show that it doesn't work. So we need to be able to justify this in general. Okay, so 1 over a to the n, let's look at examples. So this is why I'm making this distinction, because doing multiple examples and finding a pattern, it's different than doing one example and saying, in this case, it works. So this one follows from more of a pattern. And so this is a valid way of proving things in mathematics. It's called induction. That isn't very important, but just so you're aware, it's called induction, and this is a valid method of proof. Okay, so if we look at 1 equals 1 over a, or my apologies, we're not looking at that yet. If we look at a squared, this is a times a. If we look at a to the first, this is a. So how did we get from here to here? Well, we divided by a, and then it's a to the 0. So this is one of our properties, is that a to the 0 is 1. So a to the 0 is 1, and we went from a to 1 again by dividing by a. So then if this pattern continues, which it should, then we have a to the negative 1 is 1 over a, right? We divided 1 by a, and a to the negative 2 is 1 over a squared, again, dividing by a. So this is kind of where we can see this property makes sense, right? We can justify it and really believe it, that exponents follow this nice pattern of whenever you decrease the exponent, you divide by that base. So this is how you can see and justify that this a to the negative n is really 1 over a to the n. Okay, so I want to talk about these two, and lastly, I want to talk about this one. So this one is actually a definition. So it's not a property. It's more of a definition that says that if you take a and you raise it to an exponent, which is a quotient of two things, that this numerator is always going to be the power on a, and then denominator is always going to be the root on a. So if we're looking at a to the m over n, this is really a to the m times 1 over n. So you can write this in different ways. So right, if we do the m first, if we raise it to the m first, then this is the nth root of a to the m. But if we do the nth root first, this is the nth root of a to the m. These are both the same because of that associative property of multiplication, that it doesn't matter if we do the m first or the 1 over n first. These are the same thing, so that's just one thing that I wanted to point out, was that this is a definition, not necessarily a property, so you don't need to know how to justify it. And you can do these in any order because of the associative property of multiplication. So the last thing to point out whenever you're kind of thinking about these things is a lot of our examples will use our computing area, right? We've already computed area a lot. But one thing to notice is that a to the second power is called a squared, and a to the third power is called a cubed. And this exactly corresponds with geometry. So this may be something that you want to point out to your students, like I'm pointing it out to you now. that a to the second is a squared because it can represent the square area, and which is two-dimensional, and a to the third power is called a cubed, which represents this volume, which is three-dimensional. Okay, so that is all for exponents. Next time, we will start talking about order of operations. So that is all for this video.